Okay, here we're told that we're going to perform a test of a model tractor trailer rig in a wind tunnel. And we're told that the drag force is dependent on the frontal projected area of the truck. So that's the area you'd see looking from the front here. The wind speed, the air density, and the air viscosity. And the model scale is 1 to 4, meaning that a 1 meter in the model is equal to 4 meters in the prototype. The prototype, remember, is the full scale device. The model is what you'd put in the wind tunnel. The frontal area of the model is given here, and we're asked to obtain a set of dimensionless parameters suitable to characterize the model test results. And then we're told that if the drag force on the full-scale vehicle traveling at 22 meters roughly per second is to be predicted from the model testing, what should be the model, the wind tunnel airspeed for the model? We're asked to find that. And then we're told to assume that the air conditions are the same between the model and the prototype. And then when tested at that wind speed and found in part B, the measured drag force on the model was given by this, about 2.5 kilonewtons. Estimate the aerodynamic drag force on the full-scale vehicle and the power needed to overcome the full-scale drag force. So basically what we're doing here is we're making a 1/4 scale model. We're putting it in the wind tunnel, as you can see here. We need to figure out what velocity we need to put in the wind tunnel. So what's the velocity for the model, given what the prototype velocity would be. And once we measure the drag force on this vehicle, how does that drag force scale up to the real life situation? By the way, you can see here a nice example of flow visualization. And what kind of flow visualization is that? I'll let you think about it for a second. It's actually a streak line. If it's a steady flow, which it probably is in this situation, then it's equivalent to a streamline or a path line. But it's technically a streak line because it's tracing out all the fluid particles that passed through the end of the smoke wand that generated that streak line. Okay, well anyway, that's a different problem. So let's first of all start with finding the dimensionless parameters used to characterize the model test results. So this is a dimensional analysis. So step 1 is to write down the functional relationship in dimensional terms. So the drag force, we're told, is a function of the frontal area A, the wind speed V, air density, and air viscosity. That's all given sort of right here in this sentence. That's often the hardest part of any dimensional analysis problem, is figuring out what variables are the significant ones. You only get that through experience and practice, and occasionally through trial and error, maybe some preliminary experiments. It can be very difficult to get that relationship, but we're giving it to you here, so that's good. Okay, step 2 in the dimensional analysis is to write out what the basic dimensions are for each of the variables that we had in step 1. So the drag force would just be, of course, a force, which in terms of mass, length, and time would be like a mass length over time squared. The dimensions of area would be like length squared. Dimensions of density, mass over length cubed. And dimensions of viscosity are going to be mass over length time. So the reason I wrote force in terms of mass over length, mass, length, and time here is because I saw that I have a density here, and it's easier for me to think of density in mass and length rather than trying to convert it over to a force. So I just want to make sure that I have all independent basic dimensions here. Mass, length, and time are all independent. Force, mass, length, and time are not independent because you can get a force from the mass, length, and time. So I just wanted to make sure everything's in terms of independent basic dimensions. The dimensions of dynamic viscosity, you can work that out. For example, for dynamic viscosity, that has units of like a Pascal second. Pascal second is like a Newton per meter squared times a second. A Newton is kilogram meter per second squared. Let me divide that by meter squared times a second. So you can see what we're left with is like a mass. This meter cancels out with that one, and this second cancels out with that one, so it'll be mass over length time. So that's how I can figure that out. just from the typical units of viscosity. So that's how I got there. I've done enough of these problems that I just have memorized what the dimensions of dynamic viscosity are. Okay, so we have now, let's see, oh, and I missed one, velocity, v, that's length over time. Okay, so that's step 2. Step 3 is to determine the number of pi terms, or dimensionless terms, using the Buckingham pi theorem. So it's equal to the number of variables that we started with, minus the number of reference dimensions used to describe those variables. So the number of variables is up here. We have 1, 2, 3, 4, 5. The number of pi terms, or I'm sorry, the number of reference dimensions used to describe those variables, well, clearly we'll need a length because of that. We'll definitely need a mass because of this one. And we definitely need a time here. This already has mass, length, and time. This already has mass, length, and time. So we'll need 3 reference dimensions, mass, length, and time. So we'll have 2 pi terms, ultimately 2 dimensionless terms. So now we need to find those pi terms, and we'll use the method of repeating variables. So that means we need to choose some repeating variables that will make the non-repeating variables, that we'll use to make the non-repeating variables dimensionless. The number of repeating variables is equal to the number of reference dimensions. So we'll have 3 repeating variables. When you choose repeating variables, you want to make sure you're choosing them from the right-hand side of the equation. Don't make the drag force one of your repeating variables, because this is your dependent variable, and you don't want it buried inside your pi terms. You want to use the independent variables in your pi terms. And you want to make sure that the repeating variables you choose allow you to make the other terms dimensionless. So I need to make sure my reference dimensions are all expressed independently in my repeating variables. So what I'll use for my repeating variables here will be area, because that involves the length squared. I'll also choose the velocity, because that involves a time independently. And then I'll choose the density, because that has a mass in there. Now your set of repeating variables may look different from mine, but we should each have 3 repeating variables, and we should each have predicted that there will be 2 pi terms. Okay, but the choice of repeating variables is not unique. All right, so now we need to make the other terms dimensionless using these repeating variables. So the first pi term will involve the drag force. So we'll multiply it by our repeating variables, each raised to a power. And then we'll need to find what those powers are based on the dimensions. So my reference dimensions are mass, length, and time. So a pi term is dimensionless, so it'll be like the mass raised to the 0 power, L raised to the 0 power, T raised to the 0 power, because anything raised to a 0 power is just equal to 1. So the pi term is dimensionless there. There are no dimensions that show up because they're all raised to the 0 power. The dimensions of the drag force term would be like mass, length over time squared. Area, of course, is length squared. That's raised to the A. Velocity is length over time raised to the B. Density is mass over length cubed raised to the C. So now what we'll do is we'll gather all the mass terms, length terms, and time terms separately. So mass terms, and we have a 0 in the exponent over on the left side. The right-hand side, we have a mass to the 1 and a mass to the C. So it'll be 1 plus C. I'm just using the exponents here so that I can make sure that my masses all cancel out ultimately from both sides of the equation. Okay, and then we'll do the length next. So 0 on the left. On the right-hand side, we have a 1 plus 2a plus b minus 3c. So here's the 0. This is the length to the 1. Here's length to the 2a. When you raise something to a power and then raise that to a power, it's like multiplying them together. Here's length to the b. And this is the 3c here because it's length cubed in the denominator. So that gives you the minus 3 and then raised to the c there. And then we have the times. 0 on the left, minus 2 minus b on the right. So here's my minus 2, here's my minus b. All right, so we can solve for our variables here. So c is going to be minus 1. B is going to be minus 2. And if I plug those into here, so C is minus 1, that makes that positive 3, minus 2, so that's a positive 1. That makes it a 2. So A will be a minus 1, if I've worked that out correctly. Okay, so now let's go ahead and substitute back in to rewrite our pi term, our first pi term. So it'll be FD times A to the minus 1, V to the minus 2, and rho to the minus 1. Or, written differently, it's the drag force over rho V squared times A. So that's my first pi term. That actually makes sense to me because, of course, we have a force in the numerator. Rho V squared looks like a dynamic pressure, so it has dimensions of pressure. And pressure times an area makes it a force. So it makes sense to me that our pi term would look like that. So our second pi term will involve the dynamic viscosity. So we follow the same procedure that we just went through with the drag force. So we'll have mass to the 0, length to the 0, t to the 0 on the left-hand side, and then we have the viscosity dimensions, or mass over length time. Area is L squared raised to the A. Velocity is length over time raised to the B. Density is mass over length cubed raised to the C. We'll again gather terms. So for mass, we have 1 plus C. Length, on the right-hand side, we'll have minus 1 plus 2A plus B minus 3C. And for the time, on the right-hand side, we have a minus 1 minus B. Okay. So what I've done there is the same procedure I did previously. Let me just focus on the length one, for example. So we have 0 on the left-hand side. Right-hand side, we have L to the minus 1. Here we have L to the 2A, so there's my 2A. L to the B, there's my B. And then minus 3C right there. All right, so from here, you'll see that C is equal to minus 1. B is equal to minus 1. And then let me plug those into the middle one here. So we have a minus 1 plus 3, so that will be a 2. Minus 1, that'll give me a 1. And then the 2A, so that'll be, A should be a minus 1/2. I think I've done that correctly. So then let's go ahead and write out our pi 2 term. It'll be mu times A to the minus 1/2 times V to the minus 1 times rho to the minus 1, or written differently, mu over square root of A times V times rho. Those are in the denominator. And I'm just going to flip that upside down. So I'm going to just rewrite my pi term a little differently. I'm going to flip it upside down so it's rho V square root of A all over mu. It's totally fine to do that. And the reason it's fine is because this is a dimensionless term. If I flip it upside down, it's still dimensionless. Totally fine. And the reason I wanted to do that is because in this form, it takes on a familiar form here. This is actually a Reynolds number. If you recall from some previous work, a Reynolds number is like a density times a velocity times a length. Well, the square root of area is a length, all divided by the dynamic viscosity. So that's actually a Reynolds number. And actually the term up here, this one involving the drag force, that's called a drag coefficient. You'll see that in a later lecture, but it has the form of what we call a drag coefficient. So our very last step, or I'm sorry, the second to last step is to make sure that these terms are all dimensionless. So let's do that. We don't want to skip that part. So the drag force units or dimensions are mass length over time squared. Then we divide through by density, so that would be like length cubed over mass. Divide through by the velocity squared, so that'd be time squared over length squared, and then divide through by the area, so that's 1 over length squared. See, the masses cancel out, time squareds cancel out, length to the 4th in the numerator and length to the 4th in the denominator, so that's all okay. And then for the Reynolds number, of course we know Reynolds number is dimensionless, but let me work that out. So it'll be mass over length cubed, that's the density, times the length over time, that's the velocity, times the square root of the area, which will just be a length, and then divided through by the dynamic viscosity, which would be like length time over mass. So you see the masses cancel, the times cancel, the L cubes cancel, so we're okay. So our very last step, I think this is step 7, is to rewrite our originally dimensional expression in dimensionless form. So we'll have our drag coefficient is a function of the Reynolds number. So there we go. So that was the first part of this problem. If you go back to the problem statement, it says obtain a set of dimensionless parameters suitable to characterize the model test results. So these are our dimensionless parameters here. So since the physics is the same between the model and the prototype, we should have the same relationship between the model and the prototype. If I have the same Reynolds number between the model and the prototype, the function is going to be the same because it's the same physics. I don't know what that function is. I just know it's the same, whether it's the model or the prototype. But if the Reynolds number is the same, and I plug it into the function, I'll get the same number. So I'll get the same drag coefficient regardless of whether it's the model or the prototype. Hopefully that makes sense to you. This is an important part of knowing how to scale results. So let me just write this down in words. If the Reynolds number, it's not really words, but an equation. So if the Reynolds number in the model and the prototype is the same, so if those are the same, then for sure I'm guaranteed that the drag coefficients will be the same between the model and the prototype. And the reason I know that is because it's the same function, because the physics are the same between the two scales. Okay, so if the pi terms are the same on the right-hand side, then I will definitely get the same dependent pi term on the left-hand side. All right, so now I need to find out what the velocity is that I need to use in my model or in my wind tunnel. So I can use my first equation here, just equating Reynolds numbers to find that velocity. So if I rearrange this, the velocity in the model will be the velocity in the prototype times, let me do some rearranging here. We have the dynamic viscosity of the prototype over the dynamic viscosity of the model. We have the density of the prototype. Wait a second, do I have this? Let me just double check. I have it the other way around, sorry. It should be the dynamic viscosity of the model over the dynamic viscosity of the prototype. There we go. Density of the prototype all over the density of the model. And then we have the square root of the, well, I'll just write it as the area of the prototype over the area of the model, and then take the square root of it. All I've done is rearrange my Reynolds number. Well, if we're using the same error in the model and the prototype, then these will just be equal to 1. Okay? And we're told that the model is a 1/4 scale model compared to the prototype. So any length in the model is 1/4 the length in the prototype, which means that the area of the model, which will be like a length squared, will be 1/16 the area in the prototype. Right, because area of the prototype is like the length of the prototype. So this would be like the length of the prototype squared. All right, so when we plug this in, we'll get the velocity in the model is the velocity of the prototype. I think we're told in the problem statement, let me go back up to it, that the full-scale vehicle travels at 22.4 meters per second. So that's the velocity in the prototype. So that was a 22.4 in the prototype, and then that'll be multiplied by the square root of 1 over 1/16. So that'll just be, this will just be equal to 4. so that the velocity we need to use in our wind tunnel will be 4 times the velocity in the prototype, which is 89.6 meters per second when you plug in the numbers. So that's the velocity we need to use in our wind tunnel. Okay, and that just comes from equating the pi term on the right-hand side of the equation here. It's just a Reynolds number. Now to find what the drag force is in the prototype, so if you recall in the problem statement, they measured the drag force in the model. And we want to know what the equivalent drag force is in the prototype. So we'll get that from this drag coefficient relationship. So let's rearrange that. Drag force prototype will be the drag force in the model times density in the prototype over the density in the model times the velocity of the, let me make sure I'm doing this right, yeah. Density of the prototype over the, the velocity of the prototype over the velocity of the model, that's squared. And then the area of the prototype over the area of the model. Well, again, we're using the same error, so the density ratio is equal to 1. We just found the ratio of velocities that was given over here. So that'll be 1 over 4, oops, 1 over 4 squared, or 1/16. And then the area ratio, we also talked about that over here. So that'll be also 1/16. Did I do that? Oh no, I'm sorry, that should be 16. I've got that flipped upside down. It should be 16 over 1. Yeah, there we go. So when you calculate that, you'll see that the 16s, cancel out, and so we're left with the drag in the prototype is actually equal to the drag in the model. So the prototype drag, full scale, will be the same as what we measure in our wind tunnel, 2.46 kilonewtons. So as long as we're operating our wind tunnel at 4 times the prototype speed, what we'll find is that the drag force between the model and the prototype will be the same. So that's how we can use our wind tunnel test to predict the force in the real life situation or the prototype situation. The last part is what kind of power is required to overcome the drag force for the prototype. So the power that we have to apply in the prototype to overcome the drag force will be the drag force, the prototype, multiplied by the velocity in the prototype. So a power is just like a force times a velocity. So we already know these values. The drag force is 2.46 kilonewtons. And the velocity we just calculated is, we were told was 22.4 meters per second. So we can plug in the numbers here, and this comes out to be 55.1 kilowatts. So that's what kind of power we would need in our full scale or prototype tractor trailer rig in order to overcome the drag force at that speed. Okay, so this is a pretty good example showing how we do scaling, how we do dimensional analysis and use that to do scaling. So the dimensional analysis gave us this kind of relationship, just how the drag force depends on the other variables, but in dimensionless form. It's really a drag coefficient as a function of the Reynolds number. And then to do the scaling, we said, well, we want to keep the Reynolds number the same. So that told us what kind of velocity we need to have. And we know that if this right-hand side is the same, then the left-hand side will be the same, whether it's the model or the prototype. So that allowed us to equate the pi terms on the left-hand side. And then we used that to find what the drag force was going to be in the prototype. And once you know the drag force and the velocity of the prototype, you can get the power. Okay, we'll go ahead and